Number 3. Okay, Alec, you want to read it for us?
Upton Chuck is riding the giant drop at Great America.
Giant drop. Okay, so here's Upton.
And then if Upton free falls for 2.6 seconds, what will be his final velocity and how far will he fall?
Okay, so again, when we think about our information here, we're going to look at our formulas. I'm looking for VF. Do I know VI?
Yes.
Oh, what is VI?
0.
Okay. Do I know A?
Yes.
9.8.
Okay, we haven't talked about this much yet, but on the Earth, objects on the Earth all accelerate down at 9.80 meters per second if you can ignore friction.
Is it 9.81?
What do we want to use as a class? We should decide 9.80 or 9.81.
9.8.
80.
9.80. We're right. You know, there is a slight variation in that around the world. Okay.
I think so. Well, I mean, in my school it used to be 9.81.
And I see some textbooks use 9.81. I see some textbooks. You know, if we were in Ecuador, it would probably be like 9.78 or something like that. There is a slight variation in that number. So let's make an executive decision right now that our G, we're going to use 9.80 meters per second squared. Okay? That is the acceleration of a falling object. And we know that. So G equals 9.80 meters per second squared. And G can be used, gravitational acceleration can be used anywhere there's an A. Okay, so I think we have all our information listed. Delta T was 2.6 seconds. We're looking for delta D and we're looking for VF. So now we look at our equations and as we're looking for VF.
Let's use the first one.
Yeah, VI plus A delta T.
Got all of it.
We've got everything there. So VF equals VI plus A delta T.
And you can
VI is a 0, so get rid of it. So our acceleration is 9.8 meters per second squared times, we fell for 2.6 seconds. What happens to our labels?
1 second crosses off.
Okay, so 1 of the seconds from down there crosses off that one, and we're left with,
Meters per second, which is a velocity.
which is a velocity. Good news. So now we'll do our math. I'm going to have
25.5, so
25.5.
26, I don't know.
Yep.
meters per second. They're moving pretty fast, right?
Mm-hmm.
Well, we just fell for 2.5 seconds. Okay. So now it says, how far did we fall? Now I've got two equations that have a delta D in them. I want to have one that I know all the other information. Well, I know both of them. So how many would say you probably want to go with the middle one because we don't have to rearrange it? Makes sense, doesn't it? Okay, so delta D is VI delta T plus 1/2 A
Changing.
delta T squared. VI was 0, so this whole term crosses off. So 1/2, so that's 1/2 times A. Well, A is actually G. 9.80 meters per second squared.
Yep.
Our time, delta T, is 2.6 seconds, but that was squared, so we got another 2.6 seconds I'm going to put in there. What happens with labels?
Seconds will cross off all
I
of
got
them.
seconds squared on the bottom, seconds times seconds on the top, they're all gone. I'm left with,
Meters, the distance.
it's good news, okay? So, this is roughly,
33.12.
and I only actually have 2 sig figs on this one, so I think 33 is about the best I can say. Oh, over here, I could only get 2 sig figs also. This was 9.80. But we only had 2 sig figs on the time, So what's our rounding rule? Was there anything after this 5?
Yeah, we rounded to it was 4.
Oh, so then we'd round down. 25 meters per second, 33 meters.
Boom.
That is problem number 3 from the miscellaneous problems.